Today we will learn the principles of isolation of metals, or you may say metal extraction or metallurgy. Metallurgy is a term which includes these principles as well as the technology for isolation of metals. We will confine only to the principle which are chemical principles which are used in isolation of metals. So, the first question is, from what we do isolation or extraction? I think human being basically completes his all needs from either from earth or from sea. So, we also get metals from earth crust. The sea is also having a huge source of metals, but at the moment they are not exploited. Those resources are still intact, not exploited by the human being or by the man. Now, in what form metal is present in earth crust? It is present several chemical forms, and all these forms can be used for extraction or not. Answer is no. Only some of the forms which are available in earth crust, they can be used for extraction of the metals. These various substances which have metals, they in general they may be called minerals. So, what are those called from which we can extract ores? Those are called ores. So, first question comes that is there any difference between the two? Answer is yes. Ore is a mineral from which metal can be extracted conveniently and economically. What does it imply? That all ores are minerals, but reverse is not true. There are large number of minerals in our earth crust from which we cannot isolate or extract metal ions. If I give you an example, the clay is a mineral which contains aluminium, but clay is not used for extraction of aluminium. What is used for extraction of aluminium is bauxite or cryolite. So, bauxite or cryolites are ores of aluminium, whereas the clay is only a mineral. Generally, ore requires enrichment before extraction. Why? From the earth crust, when a substance is mined, then it is not the ore alone. There are many other things with the ore. Mud is there, clay is there may be a moisture. So many things are present along with the ore, and all these contaminants together which are undesired in a ore, they are called gangue. So, if the ore has to be used for metal extraction, it has to be first separated from this gangue. Now, let me give you examples of some common metals and their ores. Aluminium is a very common metal. We use it for various purposes, electrical wire, utensils. Its major ore is bauxite. Zinc is another very important material or metal. It is used to make various alloys. Its principal ore is zinc blendy. You see that aluminium ore is hydroxide, oxohydroxide, and zinc blendy is zinc sulphide. If I just in a broad sense tell you, then most of the ores present in the earth crust are sulphides, majority of them are sulphides, carbonates, oxides or hydroxides. Only few ores are in the form of chlorides or sulfates. Sulphide is a very common form of ore present in the earth crust. The copper is also present in the earth crust as a copper pyrites. It is copper iron sulphide. Iron is also present as iron pyrites. Of course, other ores of iron are also there like hematite, magnetite, siderite. The first two, hematite, magnetite, are oxides. The siderite is a carbonate. Now, the question comes that how these ores are present in oxide or in sulphide form. In the earth crust long ago, when these substances were buried, there was lot of plant material which was having sulphur. There was no air, so the plant, from the plant material, the sulphur present converted these metallic species into their sulphides. Oxide is most stable chemical formulation, so it can survive in earth crust easily and it has survived for fairly long. So, large number of ores are in the form of oxides. You know that nitrates are easily decomposable, and as a result very few nitrate minerals are present in the earth crust, and as a ore their use is very limited. Now, so if we have to isolate a metal from an ore, the guiding principle is that nature of the ore decides the total process of isolation. What do I mean is that for a carbonate ore the total process will be different, for a sulphide ore the total process will be different, for a oxide ore the total process will be different. So, the nature of the ore basically controls the total isolation process. However, for any isolation process of metals from ores, there are three major steps. First is concentration of the ore. So, first thing is that all those undesirable items or materials or substances associated with the ore have to be removed, otherwise in the process they will be also converted into a form and contaminate ultimately the metal. The second thing is to isolate metal from its concentrated form. That is the second step in all processes. First is concentration of the ore, second is isolation of the metal from its concentrated ore, and third is purification or refining of the metal. So, let us start from the concentration of the ore. Concentration of the ore is a very important, and it has to be least expensive if you economically isolate a metal from a ore. And the concentration means that you have to remove the impurities, improve the concentration. That is why it is called also dressing or beneficiation of the ore. Now, here again the concentration procedure which is used depends on the nature of the ore. For different ores, different kind of procedures are used. Of course, one or two are which can be used for all the kind of ores, but the selection of the concentration procedure is dependent on ore. Now, easiest way to concentrate can be the washing. It is called hydraulic washing. The principle of this method is difference in the gravities of ore and the gangue. This is also called gravity separation. What is done in this procedure? an upward stream of running water is applied to the basically impure ore, the running water wash away the lighter gangue particles, leaving behind the heavier ones. So, this can be used for all kind of ores, but it is limited in the sense that if the concentration of the metal in the ore is small, that is gangue is in larger amount, then it does not do much benefication or much concentration of the ore. Second method of separation is called magnetic separation. It utilizes the difference in the magnetic properties of ore and its associated substances. When we can apply this magnetic method, either ore or gangue should be attracted by the magnetic field, only then we can apply this method for separation. So, this means that this method of separation has a limited application only in the condition where the ore or gangue is magnetic in nature. If both are magnetic, we cannot separate them. Now, what are the magnetic properties useful for separation? The substances, most of the substances like wood, like clothes, cotton, they are all diamagnetic in nature. What is meant by diamagnetic in nature is that if you apply a magnetic field and make this material free to move, it will go to a point where the magnetic field is minimum or least. The example is alumina. It will go to a point if the magnetic field is applied and it is allowed to move freely to a point where the magnetic field is least. There are another kind of material called paramagnetic. This paramagnetic material is basically attracted to a point where the magnetic field is maximum. In other words, diamagnetic material basically repel the magnetic lines. Magnetic field is defined in terms of the magnetic lines. It is a so magnetic force, and this force is in form of magnetic lines. So, diamagnetic material repels the magnetic line and paramagnetic material attracts the magnetic line. The examples are paramagnetic material in ilmenite or nickel, cobalt, manganese minerals which are naturally paramagnetic in nature. It is also possible that in a diamagnetic material like alumina, some iron is present because iron is paramagnetic, and overall the mineral or the ore starts to behave as a paramagnetic material, okay, but that rarely happens. Now, for separation, what is done? There is a moving belt. You can see this is the moving belt, and there is a magnetic roller. This is magnetic roller. This is magnetic. So, ore is powdered as passed through or passed on to this belt. What happens? I told you that diamagnetic material tries to concentrate at a point where the magnetic force is least. So, here away from this roller the force will be the least. So, diamagnetic material, or you may call it non-magnetic material, will concentrate here, and magnetic material or paramagnetic material will concentrate in another heap which will be closer to this magnetic roller, and as a result you can collect the two heaps, one of the non-magnetic material and another of the magnetic material. Let me remind you that this magnetic method of separation is only possible in case of those materials or those substances in which one component is paramagnetic and another component is diamagnetic. Next process of concentration is called Froth flotation process. This is specific for sulphide ores. This cannot be used for any or general kind of ore, it is limited to sulphide ore, and it removes gangue from the sulphide ore very effectively. And since the number of sulphide ores present from which we carry out the metal extraction is large in number, and consequently this Froth flotation process is very widely used. What is a froth? Froth basically, if you take a bucket, put water in this and put some surf or any surfactant, if you pass air into it, what will happen? There will be a froth. Okay. There will be a froth formed on the top. Why this froth is formed? Because the surf involves surfactants. It has two kind of ends, one is hydrophobic, another is hydrophilic. So, basically it feels happy if it is on the surface, so that its hydrophobic end is above the water and hydrophilic end is inside the water. This is a common thing. If you do not have any arrangement for passing air, you can use your hand and can shake, there will be lot of froth on the surface. A similar principle is used here. So, what we do? We take a suspension of powdered ore made in water and bubble air through it, but what you have to do? You have to add some additives, just like that the froth will not be formed. Why we have to add additives? We have to, what kind of additives we have to add? You have to add additives which help in making froth. Oil can help making froth. What we desire? We desire that our ore goes into the oil. So, we have to use a oil which converts or which extracts ore more into it than water, first. Second, it may be possible that the difference between the association of the ore with water and oil may not be that different. So, what you have to do? You have to add collectors. What these collectors are? These collectors change ore to a more oil soluble form. Change ore to a more oil soluble form. They are called collectors. They are fatty acids, they may be fatty acids, they may be xanthates. So, the principles involved by which these collectors increase the solubility of the ore in the oil is that ore has a metal ion. So, if you are using a complexing agent like xanthate, a complex will be formed. The complex may be more soluble in oil. Fatty acids may also complex with the metal ions, and they increase the solubility in oil. This increase in the solubility in oil is also called non-wettability. That is, water now reduces its effect on the ore. That is, ore is protected by the oil and it cannot be again become moisturized or wet. Now, this oil also acts a frother. If oil and water are mixed together, a froth will be formed. That is a very easily that can be very easily experimented. If you mix the oil and with water in a test tube and shake it, you will find that a froth is formed at the top of the test tube. Now, the modifiers are also utilized. What these modifiers do? If you remember, a complex, if it is neutral, it is more soluble in organic solvents, metal complex. If it is ionic, it is more soluble in water. The pH of the solution can change the solubility of this ore which is encapsulated in oil in the water. So, pH can be changed. If you add soda ash or caustic soda to the water, pH will be alkaline, and in alkaline medium it may be possible that some ore encapsulated in oil is more soluble or in oil alone, not in water. Its solubility in water is decreased. In another case, the solubility in water may be decreased by acid. You may sometimes phosphates, silicates, carbonates or surfactants, they can be also used to decrease the solubility of ore encapsulated in oil in water. So, idea is to reduce the solubility of ore encapsulated in oil in the water. Basically what we want, reduce the solubility of ore encapsulated in oil in the form of froth in water, so that we have maximum beneficiation or concentration. Its froth flotation requires a instrument. The principle of that instrument is shown in this picture. Here there is a bubbler, air bubbler. Here pulp is a mixture of oil, ore, water and all additives. This is pushed inside, and when the air comes, the froth is formed, and this froth is collected from the top of this container. Now, the pulp which has not converted into froth is passed on to another froth flotation cell. So, froth will be on the top, the pulp is flowing, and from here the pulp will move to another container. So, basically using the such kind of apparatus in a sequence, what we can do, we can enrich the ore, sulphide ore very significantly. A question can be asked that is it possible to separate two sulphide ores? This is a very valid question, because as a sulphide not only one metal will be there will be other metals. So, that contamination of the another metal will always be present if a sulphide ore has been concentrated with the help of froth flotation. The answer is yes. How? Not always, but many times it is possible to concentrate two sulphide ores simultaneously or sequentially. What is utilized? The fact which is utilized, that one ore has more solubility in oil, ore 1 has a greater solubility in oil than ore 2. So, when these two together are subjected to froth flotation, first ore 1 will be dissolved, maybe with a very small contamination of ore 2, and will be separated. The higher amount of oil will dissolve ore 2 also, and it will be sequentially concentrate it. So, by using the different solubility of ores in oil, it is possible to separate the two along with concentrating the two. What these depressants are? These depressants are basically masking agent. These are masking agents. These are generally anions. They form very stable. If you have two metals M1 and M2, the stability of the complex or salt formed with these two metals is different. With one they form a very stable complex or a salt, and with another it is basically weak. So, what happens if a suppressant is used? The metal which forms a very strong complex or salt with the depressant or suppressant, that will not be showing its properties, and only the metal which is making a very weak complex with a depressant or suppressant, that will show its properties. So, obviously, if a metal is stopped to show its properties, it will not be extracted in the oil, or its ore will not be extracted in the oil. The example is of zinc sulphide and lead sulphide. As such, if zinc sulphide or lead sulphide are handled in presence of sodium cyanide, what happens? Zinc forms a very stable, more stable complex than lead with cyanide. As a result, zinc does not manifest its properties and it does not come to froth. Lead forms a very weak complex with cyanide, and as a result it manifests its properties and goes to froth. So far we have done three methods of beneficiation or separation of the ore from the gangue. First was gravity separation, the second was magnetic separation, the third was froth flotation. Now the fourth one is leaching. This is also not a universal method. It can be only used in those cases where ore is selectively soluble in a suitable solvent and gangue is not. Okay. So, suitable solvent implies that it does not dissolve impurities. It only dissolves the ore. The example of this is leaching of alumina from bauxite. The bauxite ore, which is known for alumina, has the impurity of SiO2, silica, iron oxides, titanium oxides, right. But there is a difference between the property of alumina and the property of silica, iron oxide, titanium oxide. If you powder the ore and digest it with concentrated solution of NaOH, under these conditions, that is around 400 to 500 Kelvin temperature and a pressure 35 to 36 bar, what happens? Alumina dissolves making an aluminate. Alumina dissolves making an aluminate. The oxides of iron and titanium under these conditions, they do not dissolve significantly, and this alumina which is dissolved due to the formation of aluminate, it can be basically recovered by passing CO2. Why? Why CO2 basically pushes back the alumina dissolved in the form of aluminate to again alumina. It is because you know that carbon dioxide is acidic in nature. So, when you pass carbon dioxide, a weak acid is generated, and that weak acid generated is enough to decompose aluminate back into aluminium oxide or alumina. Now, this cannot happen with silica, because the silica is also extracted by NaOH, concentrated NaOH under similar conditions, and sodium silicate is formed, but when we pass CO2, only alumina is recovered or comes back. Silica remains in the solution, silica does not come back. So, sodium silicate remains in solution. So, now in the two steps, in the first, when we dissolved the ore in the NaOH, we reduced the concentration of impurities like iron, titanium, and while recovering back alumina from the solution, we have removed the impurities of silicon. So, this is what leaching. Now, it is possible sometimes that alumina does not immediately precipitate. In such a situation, what we do, we induce the precipitation. For inducing precipitation, a small amount of hydrated alumina is added to the solution, from which it is coming out very slowly. This added alumina acts as a center of crystallization. So, more and more amount of alumina crystallizes on this center, and the precipitation of alumina is accelerated. Then what you can do? You can filter alumina, heat it to give back Al2O3 for your further conversion into aluminum metal. Now, silver and gold, they are generally present in the earth's crust in free form generally, or in chloride form. Silver is also present in chloride form, but they are in free form. They can be separated, they are very precious metals, they can be separated using dilute solutions of NaCN and KCN. This reaction takes place. In this reaction, these two metal ions make a complex which is linear in nature, which is soluble in water. So, if you treat the ore with sodium cyanide or KCN, these two metals will go into water in the form of a complex, right. And if in the complex you add zinc, these two metals will be released. So, very easily you do not have to use in these two particular cases any further extraction of the metal from the enriched ore, but by a simple procedure of adding zinc, the two are precipitated. Isolation of metals has three aspects: concentration of ore, extraction of metal from ore, and purification of metal. You have already learned the concentration of ore. Today you will learn extraction of metal from the ore. The second part, the extraction of metal from the ore. Extraction or isolation from the ore of metal is done mostly via oxides. Let me re-emphasize via oxides. Why it is so that oxides are preferred over all other metals salts? The reason is very simple, that oxides are easy to reduce in comparison to, say for example, sulfates, phosphates, sulfides directly. The oxides are most easy to reduce. That is the reason that we prefer oxides for extraction of metals. So, extraction of metals has two parts. First, conversion of oxide, conversion to oxide, and second, reduction of oxide. It has two parts, conversion to oxide and reduction of oxide. So, all non-oxide ores in isolation of metals are first converted to oxides. For this kind of conversion, the process, exact process, it depends on the chemical nature of ore. So, what is applicable to carbonate is not applicable to sulphide. So, chemical nature is a directing force to choose the process for conversion of ore into oxides. Commonly there are two processes which are used. One is called calcination and another is called roasting. The generally ores are available in earth crust in the form of carbonate, hydroxides, sometimes nitrate also, and largely in the form of sulphides. So, the calcination is a process which is used for carbonates, hydrated oxides, nitrates, and roasting is a process which is used for sulphides. Roasting cannot be used for oxides. Similarly, calcination cannot be used for sulphides directly, but rarely if some ores are present in the form of sulphate or phosphate, then none of these two methods can be applied for conversion into oxide. In that case, we will have to convert the sulphate into a carbonate. And for this purpose the sulphate or phosphate is fused with sodium carbonate. This converts metal into carbonate and sulphate is converted into sodium sulphate. Now, this sodium sulphate can be easily washed out with the water, leaving the metal carbonate, and this metal carbonate can be again calcined like a natural carbonate to oxides. What happens in the calcination process? If water is present or ore is in the form of hydrate, the water is removed in the form of steam or you may call it gas, and ore becomes free from hydrate. If ore is in the form of carbonate, then oxide is formed and carbonate is basically converted into carbonate, part of the ore is converted into carbon dioxide, which is again a gas. If there is a double carbonate like calcium carbonate, magnesium carbonate, then both metals are converted into their oxides and carbon dioxide is released into gas. So, we are left with only with the oxides in the calcination process, which is applicable to hydrated oxides or carbonates. In case of roasting, the ore is heated in a regular supply of air in a furnace at a temperature less than melting point of the metal. This temperature is very important. If the temperature is higher than the melting point of the metal, what will happen? Non-stoichiometric compounds or non-stoichiometric oxides will be formed and their reduction will be extremely difficult or in other words impossible. So, it is very important that temperature when the ore is heated in a regular supply of air is kept below the melting point of the metal. This means that for every sulphide the temperature will be different. Temperature is different for different metal sulfides. Or in other words, at what temperature zinc sulphide is converted into its oxide is different the temperature at which lead sulphide is converted into oxide, or cuprous or copper sulphide is converted into oxide. So, roasting is done in two ways. Sometime you can take just ore and convert it into oxide by roasting. Sometime you have to add a additive. You will learn what this additive is, but you have to add additive when the ore is just heated to convert sulphide into oxide. Now, let us take the example where an additive is required. In case of ore copper pyrites, there is a mixed sulphide CuFeS2. We do not want Fe converted into oxide to go along with copper oxide. So, what we want is that in the process of the roasting Fe or iron is removed. So, what is done, basically silica is added as a additive in the course of roasting, and what this silica does, oxygen converts first the copper pyrites into copper sulphide, iron sulphide, sulfur dioxide, because sulfur is in excess, and then sulphides are converted into oxide, but the oxide of iron combines with silica forming a slag which is iron silicate. It is a slag. Now, this slag is removed and we are left with only copper oxide formed here. This copper oxide again combined with iron sulphide gives you iron oxide, this iron oxide recombines with silica. So, this cycle goes on and ultimately finally iron is removed as a silicate slag and we are left with copper oxide. Now, where we do this roasting? For this roasting a special furnace is required which is called reverberatory furnace. This diagram shows you the reverberatory furnace. Thank you very much.